So welcome to the fourth lecture on quantum field theory. So today we are going to talk about scalar field theory. So we can think of a classical field theory as the continuum limit of a discrete system of coupled individual smaller systems. So for example, consider the classical mechanics Lagrangian, where you have, say, n systems. So your index goes from 1 to n. And every system, say, which is a particle, has some kinetic energy, which is given by the usual half mq dot squared. Q dot is the generalized velocity. And of course, this is going to be a function of time. And then between all the different particles, and we sum over all the particles, supposed to avoid overcounting, we have some sort of order in which we count the particles, and there is some interaction potential between the particles. So this is the Lagrangian, and we can derive from this Lagrangian the Euler-Lagrange equations. So the Euler-Lagrange equations, so those are the equations which are the equations of motion, and they can be derived from demanding that the physical trajectory minimizes the action. Okay, more about that later. But let's just recall the Euler-Lagrange equation. So the Euler-Lagrange equation for a multi-particle system is going to be given by this. So a classical field theory is kind of a continuous version of this. So for example, we can talk about a one-dimensional field theory. An example of a one-dimensional field theory would be a taut string whose displacement is given by y. So y is a function of x and t. And the Lagrangian of such a string will be given by, so there'll be an integral over all the x's. So what is happening here is that if you look at the discrete system, there was a sum over all the different, sorry, there should have been I here. There was a sum over all the different particles. Here, that sum is replaced by an integral over x. So every point on the string can be thought of as an individual particle, and that these particles are interacting with the neighboring particles. So, it is known that the Lagrangian density, so this is the Lagrangian. And this is called the Lagrangian density for obvious reasons. So the Lagrangian is the difference between the kinetic energy and the potential energy. And therefore, the Lagrangian density is a difference between the kinetic energy per unit length minus the potential energy per unit length. A very simple illustration of a classical field theory is that of a taut string. So we have a one-dimensional taut string whose displacement is given by y, and it's a function of x, which is the coordinate on the string, and t. So the Lagrangian density of such a string is given by its kinetic energy density minus its potential energy density. So the kinetic energy density is going to be given by half times the mass per unit length times the time variation of the displacement squared, and the potential energy density will be given by half times the tension times the spatial variation of the displacement squared. So we shall return to this Lagrangian in a moment. In general, a Lagrangian density is a function of the variable, the displacement or whatever the fundamental variable is, as well as its spatial and temporal derivative. So it will be a function of y, y dot, as well as y prime. So this is the Lagrangian density. Then the Lagrangian is going to be given by the integral of the Lagrangian density over its spatial coordinates. In our case, it's only one dimensions. And then the action is then given by the time integral of the Lagrangian. According to the principle of least action, the physical trajectory taken by the particle or taken by the system, which will be some function y of x and t in this case, that is the trajectory, the physical trajectory will minimize this action. In other words, to find this thing, we have to solve the variational equation where delta S is equals to 0. And subject to the boundary conditions that delta of y at the boundaries, which in our case, if it's a string of length, say L, means that at x equals to 0 and at x equals to L, the variation of the string is 0. Of course, this is going to be true as we are imagining that the ends of the strings are fixed. We also have to assume boundary condition in the time direction. And let's just assume that we choose our times in such a way that t equals to 0, as well as at some very future time, as say t equals to big T, the displacement of the string was 0. So these are the boundary condition. And then we have to consider the variation of the action. So the variation of the action means that, well, it's going to be an integral over x and t. So we can write that as d squared over x. And then the variation of the Lagrangian will be with respect to its arguments. So first, we write the variation of the Lagrangian with respect to y. So that's going to be a partial derivative of L with respect to y times the variation of y. And then there'll be the variation of the Lagrangian density with respect to either both the spatial derivative as well as the time derivative. And that's what we mean by this index. This index runs over 1 and 2. And then multiplied, that would be the variation of the derivative of y. So here we see that the index I is repeated in this term, so there is an implicit summation over I in the second term. So just to remind you, this means del of I means the first component is y dot, which is del y by del t, and the second component is y prime, which is del y by del x. Okay, let us return to the variation of our action. So the action can now be rewritten. What we can do is that in the second term, we can use the fact that the partial derivative and the variation of a function, they commute. So this is equal to del, variation of y. using this, what we can do is that we can rewrite this thing in terms of in this way, and then we can do an integration by parts. If you do this, well, the first term, we are not touching that, so it remains what it is. But the second term now, we get one term which is a total derivative now. So we get del of I, partial derivative of L, the Lagrangian density with respect to del I of y, times the variation of y, and then we get a minus of the divergence of del L by del Iy, and then times delta y. So these are the three terms we have. Now, if you look at the second term, this is a total derivative term. So we can do an integration. We can integrate, and what will happen is that it'll become a boundary term. So the second term, so we have some space time. So this is t equals to 0, and here we have t equals to big T. That time goes that way, and space goes that way, and this was 0, and this is L. So the second term now becomes like a boundary integral over the whole boundary. But we have chosen the boundary condition over here such that delta of y goes to 0. But we see that delta y is in this, so the second term is going to be 0 as a result of our boundary condition. So as a result, we have left delta of s is equal to d squared of x, and then in the bracket we have delta L by delta y minus this we're looking at this term now, and this would be we can put a bracket here, then there's a derivative with respect to I, xi, and then we have delta L by delta I of y, and then this bracket closes, and then we have multiplying the whole thing del of y. Now, del of s equals to 0 means that this whole thing has to be 0. But we see that del of y are arbitrary. They're small but arbitrary. So if this is to be true, it has to be that the integrand always have to be equal to 0 no matter what. The integrand is identically 0, which means we get delta L by delta y minus del y del L by del Iy equals to 0. So this is the Euler-Lagrange equation, but for a classical field, for a classical field theory. So now that we have the Euler-Lagrange equation, which is given by this, we can evaluate what the equation of motion is going to be for our one-dimensional field theory, the string. So the string had its Lagrangian, remember, it had the kinetic term as well as the potential term. So this is a Lagrangian where the Lagrangian does not depend on the displacement. And therefore, the first term in the Euler-Lagrange equation is going to be 0. But there'll be two terms contributing to the second term. And so we will have delta L by delta y dot. That's going to be mu y dot. And then there'll be delta L by del y prime. And that's going to be minus t y prime. And of course, for the equation of motion, we have to take another derivative. And then this becomes the equation of motion becomes mu y double dot minus t y double prime equals to 0, which we can write as mu over t y double dot is equal to y double prime, or we can write it more explicitly as del squared y by del x squared, and then del squared y by del t squared with 1 over v squared, where v is given by square root of t over mu, and v is the speed of waves on the string. And by dimensional analysis, you can show that the right-hand side of this does have the dimension of speed. So this is a very simple example of a classical field theory.